All right, let's do a problem with continuous compound interest. Okay, so here's our nice little formula here. So what continuous compound interest, this is a similar idea to what we did in the last one with just regular old compound interest. We're taking the interest on the interest, on the interest, on the interest, on the interest, on the interest. Where before we were taking it a finite number of times, right? We were like, just if we have the nice formula for the regular compound interest, we had the number of compoundings per year. The idea that was happening with that n was we were going to add the interest to our existing principal that many times per year. Now with this one, we are going to continuously compound the interest. So what that's saying is mathematically we're gonna make the n from this other nice formula, we're gonna make that go toward infinity. But that kind of gets into talking about limits and things that are beyond the scope of this course. So what's happening essentially with this is that the interest is just continuously being added to the principal. There's never a point where it's not. It's just the interest just gets added to the principal all the time. So anyway, we've got pretty much the same little variables with this formula. The A is still the amount after t years. P is still the principal, so that's the initial amount we start with. R is the rate per year. Again, per year is the big deal there. And T is the number of years. Okay, well, let's look at this problem. So when practically speaking, when we look at these problems, we want to look for these keywords, right? We want to say compounded continuously. So then immediately that's going to light a bulb in my head and say, oh, continuous compound interest. So I know that I use this nice guy here. So we got continuous compound interest. We got $2,000 invested in an account earning 7.5%, compounded continuously. How much is in the account after 8 years? Okay, well, let's do this the same way we did the other problems on the just regular compound. Let's just identify all these variables. So for the first one, A, this is what we want, right? How much is in the account after 8 years? So we don't know what that is. Our principal, we do know what that is. That's 2,000. Great. Then we put the rate. This is per year, 7.5%. And we're going to want to write 0.075 for that. And then our T is our time. We're going to have 8 years for this one. So for the first problem, we can set this up, right? So our nice formula here, A of T is P. So now we can just plug in what we've got. So A of 8 is our principal times E to the power of the rate times the time. So we got the rate times the time. So this is 0.075 times 8. And we can do that. So I didn't do this ahead of time like I really should have. So I'm going to crank this through the calculator right now. And you can do that as well. Right. So 2,000.075 times 8. Right, so that's really, it's just kind of calculator work, and we can round to the nearest cent here. I got 3644.24. So our investment compounded continuously after 8 years will be worth $3,644.24. Okay, and again, once we get to this point, all that remains is really calculator work. Okay, so we can do the second part. How long will it take for the investment to double? Okay, so let's do this just the same way we did here. So A, this is the amount that we want. So how much would that be if we doubled what we started with? Well, we started with $2,000. Okay, so to double that, we would want twice that. So that would be 2 times 2,000, which would be 4,000. Okay, that's, again, dollars. Okay, our principal is 2,000. Our rate is still 0.075. And our t is the thing we're after this time. So now we can just plop it on in the nice formula. Here's the nice formula. So A of t is equal to 4,000. And that's equal to the principal, so 2,000, times e raised to the power of the rate times the time. So we got the rate, 0.075, and we've got a t. Okay, so if there's a hard part of this problem, here's the hard part. We just want to solve this for t, and we can, we can do it. We're going to do kind of the same thing we did in the previous problem, where we first have to realize we want to get this term alone, right? We're trying to isolate t, so we want to first get this term containing t alone. So we'll divide both sides by 2,000. So 4,000 divided by 2,000 is 2,000, or excuse me, it's 2 equals e to the 0.075 t. All right. Now at this point, we're going to be a little bit tricky, and we're going to use those properties of logarithms to say that we can apply a natural log to both sides, and that still has to be equal. And now we can use the beautiful, I think it's the, I forget what they call it in this textbook, but it's essentially an exponent rule. It changes the exponent into a factor. So we're going to take the exponent position and tack it right in front. So the left-hand side of this doesn't change, but the right-hand side, we're going to write this as a factor out front now. So we got 0.075 t times the natural log of e. Okay, so natural log of e, that's just 1, isn't it? And that's another one of those properties of logarithm. So what we've got is natural log of 2 equal 0.075 t. And we can use this to solve just directly for t, right? T is going to be, we're just going to divide both sides by 0.075. So we've got natural log of 2 over 0.075. Now this is where we get to the calculator work part, and we can do the calculator work there and find that this is rounded to 3 decimal places here. That's 9.242 years. And we're done.